for this invitation. I hope that this talk will be of a finite simple group. So you sort of see an example of such an equation in the subtitle. On the left-hand side, you have variables. Here, they're called x and y. If there are more of them, I'll just call them x1 through xn. On the right-hand side, you have a constant, which is an element of the group. And the question is whether there are elements x and y in the group such that the equation has a solution. So that's the general question that I want to talk about. So let's see. So the setup, yes, as I said, G is a finite simple group. We have the variables as a word in terms of these variables, but also the inverses of the variables are allowed. And then we have a constant, as it were, an element G in G. And we want to know whether this equation can be solved in G. The kind of typical situation that I'm thinking about, I fix the word, and so I fix the left-hand side, and I'm interested in different possibilities for the right-hand side. I mean, the kind of best situation would be that maybe I'll go back here. The best situation is that for all elements G, there will be a solution of this equation where x1 through xn lie in G. And that can be expressed in this way. You see, the element W, the word, defines a function from G to the n to G. It's not in general a homomorphism, but a function where you just evaluate W at the n tuple of elements in G, and you get an element of G, and as the result, and you want to know whether this is surjective. And kind of typical thing which you expect to usually happen, at least I think that that's the expectation that most people have, is that for most W, what happens is that if G is large enough, this map will be surjective. That seems to be the most usual behavior as far as anybody can tell. In fact, if you think about it this way, if you think about W as being a somewhat kind of a randomizing function, it sort of mixes up these group elements in some way that's sort of random, which how good that model is not clear. But if you think about it in this way, then at least if n is bigger than 1, then this set G to the n is much bigger than this set G. And so you would expect each element to be hit, probably a lot of times. In fact, you would expect approximately the order of G to the power of n minus 1 solutions for each G. So is that true? Okay, before I talk about finite groups, I want to talk about something which sounds harder, but is actually easier. Alternating groups. These are the first ones discovered, the permutations in n elements which are even. As long as n is greater than or equal to 5, this is a simple group. And now there's a collection of, I think they're more interesting groups, which are said to be of Lie type. And morally speaking, if you forget about these p's, ignore the p for a moment. Morally speaking, the way I think about these groups is you have a complex simple Lie group, but instead of plugging in complex numbers, you plug in elements of a finite field. So for example, we talked about SLN, I guess it was maybe M before, but anyway, SLN, we talked about it before. For us, it doesn't matter so much because mostly we're interested in things which are true for large finite simple groups. And so I can just assume that they're too big to be sporadic. So that's the classification as far as we're going to need it here. We do not consider cyclic groups of prime order to be simple groups. I mean, they are, I guess, but the theory of polynomial telling in some sense, I would like to be saying something about a general theory, but we don't really know anything about the general theory. So instead of talking about what happens with general words, I'm going to talk about several different families of words where we do understand what happens. And what happens is different in the different families, and the methods are different. And okay, so let me just quickly say, what is a free group? So let's say, for example, the free group on generators X and Y would consist of all words which are formed out of X's, Y's, X inverses, and Y inverses, where the only relation is that when a symbol is next to its inverse, you can cancel them. So like Y, X, X inverse Y would be the same thing as Y squared. Okay, so that's the free group on 2 generators, and in n generators, it's the same thing. Just you have more symbols to form the words. Now, what is a basis? So if you have the free group on well, say you have the free group on 2 generators, a basis would consist of 2 elements which generate the group. And if you have n elements which generate a free group of order n, then it turns out they have no relations between them. There's sort of an analogy between free groups and free abelian groups, like z to the n, where if you had, I claim that there is a unique solution in x and y to the system of equations. And the way that you would determine it is you would say, well, because x, y, x is equal to g, therefore x, y solutions corresponding to all the possibilities for h. Likewise, if we just look at the second equation, there are exactly order of g solutions. So that's the story for primitive words. Now, at the opposite end of the spectrum, I would say, we have the power words. So what is the deal with power words? A power word is, we take a word v, which of course should be non-trivial, which are greater than or equal to 2. And when we do that, we end up with a word like xy, xy. And what we see about these words, well, the Feit-Thompson odd order theorem says that every simple group, kind of atypical example, so we say that W is of nu, where W1 and W2 have no variables in common. So for example, we couldn't say XY, XY is of Waring type, because if W1 is XY and W2 is XY, they have 2 variables. If I look at the image of a word map, like W1, I claim that this is always a union of conjugacy classes. So let's think about that in the case of something like x squared. Why is it that the elements which are squares consist of a union of conjugacy classes? Why is it that if one element is square, all of its conjugates are square? The reason is that if we take x squared and we compare that to what we would have gotten if we first conjugated x by something, say z, and then square, it's the same thing as squaring and then conjugating. So if we square and then conjugate, if we have a square and we take a conjugate, it's the same thing as a square of some other element. And that would be true in general for any word. So the nice thing about a situation like x squared, y squared, is that this is going to be a union of products of conjugacy classes. And products of conjugacy classes are relatively easy kinds of sets to analyze in group theory. Right? So if W1 takes a value in C1 and W2 takes a value in C2, then W1, W2 takes every value in C1, C2. So which values are there for this? Okay, we're going to get to that in a minute. But first, I want to mention one other class of examples, of which the best example, if W, the word map W, is surjective. This result is nice if we just want analogous statement. The statement about equidistribution wouldn't be true if we didn't n, where each of the wi's involves a distinct set of variables from any of the others. Those are the kind of words we want to look at. And then the question is, how big does n have to be? And to decide how big n needs to be, what you do is you look at the maximal length of the wi's. So for example, if I say that I'm interested in 4th powers, then the maximal length of the wi's would be 4, and then I could think how large n has to be. And in fact, n grows, roughly speaking, as the 4th power of the maximal length of the wi's. So with some constant times 4 to the 4th, if n is bigger than some constant times 4 to the 4th, and we look at a product of n 4th powers, then what we see is that the number of solutions, the number of ways of representing g as a product of, let's say, 1,000,000 4th powers, tends asymptotically to g to the power of whatever, 999,999. And this convergence is actually uniform in g as g goes to infinity. Now, when we talk about normal algebraic groups, it makes sense, normal algebraic subgroups, and so it makes sense to talk about simple algebraic groups. Another thing which I more or less said about algebraic groups, although I didn't say it in this language, is that an algebraic group can be thought of as a functor, is approximately q to the n, and this approximation gets good if we fix the variety and send fq to infinity. remember when I drew this picture and I had a horizontal axis where FQ is going to infinity, and I said you could use algebraic geometry. So this is the kind of algebraic geometry you can use. Now, or algebraic closure. The point is that if a variety has several different components, then each of those components should have about q to the n points. So you couldn't expect that q to the n would be the right number. Yeah, when we have an algebraic subvariety of g to the n, that number of points satisfying this polynomial equation. And the point is that the subvariety that I have in mind is going to be the inverse image. So remember, I'm trying to solve an equation with g on the right-hand side. And so I can look at all the n tuples where w evaluated at this n tuple gives g. That gives me some polynomial equations, and that defines a subvariety x. And I can use Langevin to show that when q is big, there are going to be solutions in this equation. So this gives me a kind of an algebraic geometry approach to showing to showing that Waring type problem, it's not circular, it's non-empty for most g. And here's a question that I would very much like to know the answer to. Are most words good for all simple algebraic groups? I mean, up till now, we've been talking about very special families of groups, which are very special families of words, which are rare, all simple algebraic groups G. I just say that if you give me, and I see that I am still well within my time. Yes, I timed this as a 50-minute talk, but I am done. We begin with large fields, which maybe of all the three are the ones which need most explanation. And it's always been a theorem which I think is one of the most beautiful theorems in number theory. And it says that if you have a number field and if you have a curve x over this field, and if the genus of the curve is greater than 1, then the number of points over the field, the number of points of x, which are defined over the field, will be finite. So a large field is sort of at the opposite extreme from a number field. Singular curve, x over k, one of two things is true. Either or there are infinitely many. Now, this is, I think, maybe a somewhat strange looking definition. And I'm going to talk about a few examples, and I hope that the sense of it will come through when we talk about examples. But I just want to say that, audience still, don't worry about it. It's not going to be essential for the talk. Okay, here's another class of fields. Suppose you have a field which is infinite, but in which, if you don't know what an ultra product is, don't worry about it. But if you do, then ultra products of finite fields would be another example. Okay, and each of these examples has finitely generated absolute Galois group. In the case of, so what do I mean by absolute Galois group? What I mean is you take, okay, if you're in characteristic 0, you take the Galois group of the algebraic closure over your field. If you're in characteristic P, let's assume that the field K is perfect. If you want, just make it characteristic 0 and don't worry about it. And then assume that the Galois group is a pro-P group, so an inverse limit of finite P groups. If this happens, then K is large automatically. And that's true even if this pro-P group is not finitely generated. I mean, I think, and it seems to me that that this theorem and the examples are suggestive, although they don't prove anything. I think that there is some connection between the absolute and this Galois group is finitely generated. Then K is large. Okay, let me move on to this result of Pham and Peterson, which. But before I do that, I had it, so I want to say something about abelian. So for me, a projective variety means something which, first of all, is given in projective space by homogeneous polynomial equations. So I talked in my previous talk about affine varieties, so that then you just have n variables and you have some polynomial equations and you look at the solution set. Projective varieties, I would have, if I'm this is kind of the big fact about abelian varieties and abelian varieties in number theory as well. But this is sort of the starting point without which the whole theory falls apart. Whereas, for example, if you have an abelian variety over an algebraically closed field, generally this is not true. It's generally not. So the theorem that Fehm and Peterson proved is that if you have a large field, which is not locally finite, and I think I wrote something, point in this talk is a billion varieties. I'm assuming everybody knows what a Galois group is. I've explained largeness, but I haven't explained a billion varieties in my slides, and I should have done so. Once you've found infinitely many points, you need to show that they're independent of each other, right? I mean, there's more than one step. But the hard part is to find a source, an infinite source of points on your billion, right? In this funny sense that there's a finite collection of elements which generates a dense subgroup in GK, or equivalently, that every finite Galois extension, gal L over K, has a bounded number of generators, independent of what L is. Under that hypothesis, the conjecture is that every A over K has infinite rank. That's the conjecture. So I made this conjecture before Fehm and Peterson proved their theorem, but now this conjecture sort of became part of the general story of what people expect in the world of large fields. Okay, now, so I claim that we can find lots of points in A of K. It's not locally finite, but the absolute Galois group is finitely generated. Then, not only, okay, so what can we do? What we can do is we can take the points of A over the separable closure of K and turn it into a vector space over C by tensoring over C. Okay, now the Galois group acts on the coordinates of these points because this GK is just the Galois group of K sep over K, so it acts on the coordinates. So GK is a group of automorphisms, well, acts as automorphisms on this A K sep, and therefore it acts linearly on this complex vector space. It also acts continuously. And you can ask, what is this representation? And so it's not difficult to see that the representation will be a direct sum of irreducible representations, irreducible complex representations of GK, each of which is continuous. So the conjecture is, that every irreducible complex continuous representation appears with infinite multiplicity. If you think about the trivial representation appearing with infinite multiplicity exactly means that when we take A of K, that has infinite rank. So this tells you that not only does the trivial representation appear infinitely many times, all complex continuous irreducible representations appear infinitely many times. That's the conjecture. Okay. The other thing is we say that GK is cyclic, and we really just wanted to say it's finitely generated. So this is only the one generator version. We would like to do this for the n generator case, but we said before that E of K is an infinite rank. She proved something stronger, which is the subgroup, which is sort of understandable in the sense that it comes from geometry, from these Heegner points. All the other constructions that I talked about today, we don't really know where the points are coming from. I mean, in some sense. But here, these points are sort of given to us by arithmetic. And so for me, this is a very, very satisfactory result. Again, the weakness is it does assume the Birch-Swinnerton Dyer. Of course, the fact that this theorem is true, assuming Birch-Swinnerton Dyer, is very strong evidence that it should be true. But there's still additional hypotheses, either the existence of a real place, or in the totally imaginary case, they can do it by assuming a non-integral J in fact. And yeah, that's all I have to say. Thank you for coming to the talk.